almost live. Okay, now I'm live. So first of all, I wanted to do a short apology. I'm not quite done with the test yet. And so I'll have exams to give back on Friday. If you don't come on Fridays, but you still want your exam, feel free to just stop by outside and I'll have them. Okay, so you can just come in and get your exam and go if you want to get your exam on Friday and you're not a Friday person. Okay, so other than that though, yeah, so far so good on the exams, but not quite done putting everything in. So we will have them on Friday. Any homework questions over, I believe it's 10.1 that we are talking about today? Yes, sir.
79.
79. Sounds ominous.
It is.
Okay, 79. We have a fixed point iteration. It says a method for estimating a solution to the equation x equals f of x, known as a fixed point iteration, okay, is based on a recurrence relation. Okay, yes. Use the fixed point iteration to find a solution to the following equations with p equals 3 digits of accuracy using the given value of x0. All right. So what they're saying is we let x0 start as something, and then we iterate this thing by pumping it through a function to get new iterations. Okay, so let me see what we got here. So what 79 says is we have x equals cosine x is the function that we're using to iterate here. And we have x0 is equal to 0.8. Okay, so what this is saying to do is we have our x0, and then the way that we're going to get x1 is we're going to plug x0 into f of x. So to get x1, we're going to say, well, x1 is going to be equal to cosine of x0. But x0 was 0.8, so this is cosine of 0.8. And so here we're going to have to use a calculator or something to actually compute what is cosine of 0.8. And I think it's going to probably be fairly important to us that we use radians and not degrees. Okay, so did anybody do this? So what's cosine of 0.8?
.6967067.
Okay, so 0.6967, you said?
Yes.
Okay, so let me just read this just to be sure I'm loving it here. Right. Right. Okay. Yeah, so what we're doing is we're creating a sequence of values. So we got this second value, and now we could say, okay, so what's x2? So x2 would be cosine of x1, correct? And so what's x1? Well, we said that x1 was 0.6967. And do we get anything?
And it gets 0.76696.
0.766. Well, let's just call it 7.
Okay.
Okay, and then we say, well, what's x3? Well, that's cosine of x2, which is equal to what?
0.7199.
0.7199?
Yeah.
Okay, what's x4? It's cosine of 0.7199, which is what?
0.7518.
And the question here is, as we iterate this, we go to x5 and we get cosine of 0.7518. What's that, by the way?
0.7304.
Are we actually getting close to something, or is this just a big fat mess? Well, it actually seems like, okay, I was at 0.8, then I was below 0.7, then I was above 0.7, then I was actually just a low 0.71, then I was 0.75, then I was 0.73. It seems like maybe I'm getting close to something. Does everybody agree? So what if I kept going? So just keep doing this. And I get cosine of what? I guess 0.7304, let's say. What's that?
0.7449.
That's good, right? Keep going. And the question is, do I ever get to a place where basically the first 3 decimals are the same? Do you see what I'm saying? So if I kept going, am I getting close to something where it's the same thing when I plug it in again? Because ultimately what we're saying is there a place where x and cosine of x are actually the same thing? Right? And if there is, that's what we call a fixed point. Okay, that cosine of x doesn't actually do anything to x. So, and if there is, what is it? So keep going, and what would we get? Let's see, x7 would be cosine of 0.7449, and what do we get?
0.7351.
0.7351. And of course, I'm losing. Every time I do this, I'm introducing a level of error because I'm not actually taking the full decimal, right? So I'm introducing error, but it's kind of sort of okay that I'm introducing this error because the error is being corrected for by the algorithm itself. It's just kind of saying we're narrowing in. So it's kind of like we're pinballing into the answer. And I just want to know what's the answer. So as long as I'm getting closer every time, it doesn't really matter that I'm introducing error by rounding things off. So I can keep going. x8 is cosine of, I suppose, 0.7351. And what's that?
0.7417.
And is that even better than this guy? I suppose it is. So x9. This is really exciting. 0.7417 would give me what?
0.7373.
And is that even bigger than this one? Yes, it is. So you can see, I don't know that I need to do this 100 more times. I don't think you have to do it 100 more times. But you keep going. And I think that what the question's asking for, let me just make sure, it says, to estimate L with p digits of accuracy, right, of the decimal, we can compute the terms of the sequence until 2 successive values agree to p digits. Right. And so it's saying use it to compute it to 3 digits of accuracy. So right now we're not there, correct? Right now we actually only have 1 digit of accuracy. And we're still going. But if you kept iterating this isn't hard to do, is it? Because you say cosine of answer, cosine of answer, cosine of answer, cosine of answer. And as soon as you do that on your calculator enough times so that it matches to 3 digits of accuracy, one time, you're done. And then you take that as your number. And so as long as you've got a calculator where you can just say cosine answer, cosine answer, cosine answer, just keep doing it until finally there's 3, it's 0.7, I'm not sure what it would be, probably 3 something, and then you're done.
Yeah, I think it's 0.739.
0.739, that seems plausible.
I just haven't got it doing
Yeah. Okay. So does that make sense to everybody? And what did we actually figure out right there? I think that's a good question. Like, what did we figure out? What we really did is we said, there's a place where x and cosine of x are the same thing. Where? Well, at about 0.739.
Yeah.
Does that make sense to everybody? Okay. Cool. Yeah, that's good. Any other questions? Yes, sir.
Did you go over 12?
12? Sure. Number 12 says, so this is consider the infinite series, evaluate the first four terms of the sequence of partial sums. That one? Yeah. Okay. First four terms of the sequence of partial sums. Yeah. So we've got number 12, we've got sum k going from 1 to infinity of 1 over k. Is that right? And then it says, let's figure out the first, evaluate the first four terms of the sequence of partial sums. Okay, what are they talking about? And this is really important. I talk about this stuff in the lectures. I'm not sure if I talked about partial sums in this lecture. Did I? I don't think so. Okay, that's okay. I can talk about it a little bit right now. So what they're talking about is, well, this is saying to add up a bunch of stuff. So this says add up 1 over 1 plus 1 over 2 plus 1 over 3 plus 1 over 4 plus, and so on. Correct? And so what does that add up to? Well, the way that we end up doing such a thing is, this is really interesting because it brings up another one of these interesting math philosophy questions. And that is, can I add up an infinite number of things? Period. Well, and if I asked you this question, it's easy, right? If I said, can I add up 2 things? Well, I certainly hope so, right? Like if I say 2 plus 2, can we do that? Yeah, it's 4. And then I could say, can I add up 3 things? And then you might say, well, sure, you can. And I say, well, how would you go about doing such a thing? And it would be right for you to say, well, we add 2 of them together, and then we take that new number and add the 3rd on, and then we can do it. And I say, so you're saying we could add up 40 things? And it's like, well, sure. Add 2 and then add 1 and then add 1 and then add 1 and do it 40 times and you'd be done. So we can add a billion things. Sure. Can you add infinite things? Well, I understand the logic of just keep adding, but can you actually do it? Can you add infinite things together? That's a good question. I don't know necessarily the answer, but what I do know is that I could add finitely many of them together. And so what we can do is we can start forming what we call a sequence of partial sums. And this is why sequences are so important. We're studying sequences right now, but the only reason we're studying sequences right now is so that we can talk about series. And this is a series where I'm adding up a bunch of stuff. And this sigma, this like Greek capital sigma, just says add some stuff up. Okay, and what I add up is 1 over k, where k starts at 1 and gets big. So 1, then 2, then 3, then 4. If you're a CS person, this is just like a really, really large for loop, right? So it just says, just for k equals 1 to infinity, add up 1 over k. So the way that I could do this, though, is I could say, well, what's the first partial sum? And what I mean by that is just take the first term and add it. So just add 1. Okay, that was easy. S2, I could add up the first 2 terms. So 1 plus a half, which is 3 halves, right? S3, I just say add up the first 3 terms. So 1 plus 1 half plus 1/3. What would that be? I guess I could get a common denominator of 6 if I wanted to. So that's 6/6 plus 3/6 plus 2/6. And then I get 6, 9, 11 over 6. Okay. S4, and I think they just wanted the first 4, correct? Is 1 plus a half plus a third plus 1/4. And then I guess I could get a common denominator of 24. So I get 24 24ths plus 12 24ths plus 8 24ths plus 6 24ths. Add them all together. What do we get? 36, 44, 50. Correct? Okay, so we got the first 4 partial sums, and we could theoretically keep going. When I do, I'm forming a sequence, right? The sequence that I'm forming right now is the sequence 1, 3 over 2, 11 over 6, 50 over 24. And the question is, what do we think of this sequence? Does it converge and add up to something? Because if it did, if the sequence here of partial sums added up to something, nice, or the limit of this sequence was going somewhere, I should say, then I could say that this infinite sum exists and is that number. If these numbers are going off to infinity or something, then we'd say, yeah, this doesn't really add up to a nice number. It diverges. Okay, and this is what we'll be talking about in sections to come a lot more than today. But it's a really interesting question, this particular one especially. So this is a series, and we'll learn more about this soon in sections to come, but this is called the harmonic series. Okay, because basically we're adding up the lengths of the harmonics on a string. And it's very interesting, and I won't spoil all the surprises around this particular problem, but it's a very interesting problem, and that's the answer for today. I have a lot more to say about the harmonic series, but I'll save it for the section on the harmonic series. Okay. Other questions? Yeah.
31.
31. Okay. 31. Okay, so we have a sequence. So 31, we've got 1, 3, 9, 27, 81. 1, 3, 9, 27, 81, and so on. And it says, find the next 2 terms, find a recurrence relation that generates the sequence, and then find an explicit formula for the nth term. Okay. So first of all, do we see a pattern? What do you think? Yeah, and so what's happening every time to get from one term to the next term? Multiply by 3. Everybody agree? So in that case, I think that coming up with the next 2 terms, not so bad. right? So what I would say is like if I called this S1, well, let's call it A1. I like that better. A1. So A1 is 1, A2 is 3, A3 is 9, A4 is 27, A5 is 81, A6, we're saying that the magic is to multiply by 3. So let's see, that would be 243. Does that sound reasonable? And then A7, let's see, would be 729.
Yep.
Okay. Sound good? Okay, so first two are done. Second thing they say, all right, can you come up then with an equivalent, a recurrence relation. And what a recurrence relation is it says, here's the first term, and here's how you get to the n plus first term from the nth term. So if I know the one that comes before, I know the next one. And you even said what it was. So how do you get to the next term? You said multiply by 3. I agree. So what I could do is I could say, the way that I could generate this infinite list is I could say, well, the first one I know, it's 1. And then the question is, what if I wanted to know the n plus first one? Then how could I generate it if I knew the one that came before it? What would I do? Multiply by 3. Multiply what by 3? A sub n. That's right. So I would say that it's 3 times A sub n. That's it. That's all I need to know to generate everything. So once I know A1 is 1, that's important because you do need to know where to start. But now I can say, well, what's A sub 2? Well, A sub 2 is 3 times A sub 1. And then what's A sub 3? Well, A sub 3 is 3 times A sub 2. And yada, yada, yada. And you could generate every single one. Does that make sense? Yeah. Okay, so that's the recurrence relation part, which is part B. Part C says, okay, this works, but it's kind of sloppy in a sense. It's also sort of powerful. How many of you are there many CS majors in here? Yeah, do you know what I mean when I'm talking about recursion? Recursion is super powerful in coding, right? But it can also like lead to some horrific situations. So you've got to be a little bit careful. So sometimes it's nice if you can just go in without using recursion. Recursion is really nice for computers, not so nice to us, because if I said to my computer, okay, given this information, what's the 100th term? The computer just goes, boom, it's there. If I say it to you, you hate me, right? So a closed form or just like a nice formula is better for us. So the question is there a way to describe like A sub n just using numbers, not having to use the one that came before? And I think there is. So, and what would it be? If you wanted the nth term, how would you generate it? Well, what are all these guys? They're powers of 3. So how would I write this so that it matches up correctly? Because 3 is not the first guy, it's the second guy. Yeah, so 3 to the n minus 1. So let's see if this works. If I plug in 1, I get 3 to the 0, which is 1. If I plug in 2, I get 3 to the first, which is 3. If I plug in 3, I get 3 squared, which is 9. Looks like it works perfectly. So this is it. So this is a way that you could use recursion to generate the next terms. This is a way where you're just like, oh, come on. What's the 100th term? Well, it's 3 to the 100 minus 1. So 3 to the 99th, and we're done. So there's power in both of these ways of generating a sequence. Sometimes one is better than the other. Sometimes you cannot find a closed form. Does anybody recognize this sequence? 1, 1, 2, 3, 5, 8, 18, 21. Is that familiar to any of you? Yeah, what's that? Yeah, this is called the Fibonacci sequence, right? And it's kind of famous. If I were to ask you, okay, what is, do the same thing, then, well, first of all, could you come up with the next term? Does everybody understand how the Fibonacci sequence works? So to get 2, I add the 2 that came before it. So 1 plus 1 is 2, 1 plus 2 is 3, 2 plus 3 is 5, 3 plus 5 is 8. By the way, has anybody ever heard of, like, if you take the ratios of like these numbers and keep going, do you know that forms a sequence? Do you know that that sequence converges? And it converges to something we call the golden ratio. Okay, so that's kind of cool if you know anything about art and the golden ratio and everything. Like the Fibonacci sequence, the ratio between neighboring members, that sequence converges to the golden ratio. So the Fibonacci sequence is very interesting in that way. It's also interesting in the way that, like, most natural things, like the sides of a banana. Have you ever counted? I'm sure you've eaten plenty of bananas. How many sides are there? You know, so it makes me very sad. Sherlock Holmes would not be proud. But let's see, I believe there are 5. Okay, and so it ends up, and even on very complicated flowers and things with lots of petals, if you really, like, sometimes a petal falls off, right? So it isn't always perfectly accurate, but typically in nature, the number of petals or the number of sides or the number of, like, twists on, like, a pineapple or something, it's in the Fibonacci sequence. And why? I don't know, but it is. So that's really interesting. So this is a really fun sequence to study, but the question is, could I write it recursively? The answer is yes, but you can't just use the guy before. In fact, we defined it when I said how you compute this sequence. I told it to you recursively. So tell me, what numbers do you need to know to get started with the Fibonacci sequence? Yeah, you actually need to know the first 2, because the third one is the sum of the first 2. So I would define it as A1 is 1, A2 is 1, and then I can define what A sub n is. What would the nth term of the Fibonacci sequence be? Yeah, sum the 2 that came before. So I could say that it's A sub n minus 1 plus A sub n minus 2. Now, if I wanted to say, well, what's A3? Then A3 is equal to A2 plus A1, which in this case is 2. Right? And then I could say, well, what's A4? Well, it's A3 plus A2, which is, well, A3 was 2 and A2 was 1, so it must be 3. And you can keep going. Okay, so unfortunately, the Fibonacci sequence doesn't have a nice closed form, where it's just like, what's the 100th term of the Fibonacci sequence? It's like, well, that's not very nice. And there's no way to make it nice. You just would have to keep adding like 100 times to get there. So this is a very easy problem for a computer. a very hard problem for a human if they're just, bored on a Sunday afternoon. You know what I mean? It's not pleasant. So some sequences are very easy to write using recursion, impossible to write using a closed form, which is just like, what's the nth term? That. And some we can use a closed form, but it's very hard to write it using recursion. Does that make sense? Yeah.
Question 32, I think the recursion formula, I got confused on that.
Okay, which one?
32.
32. Okay, let's take a look.
That's you.
So 1, 4, 9, 16, 25. Oh, yeah.
I don't know how you do it. Yeah.
So we've got 1, 4, 9, 16, 25, and so on. Okay, and then we want recursion and closed form. And you were saying you like closed form.
Yeah.
Yeah, me too. So the closed form is pretty straightforward. A sub n would be what?
That's right.
N squared. Because the first term is 1 squared. The second term is 2 squared. The third term is 3 squared, yada, yada. The question is, well, what about recursion? Interesting. Okay, so how do I get from 1 to 4? There's a lot of ways, but one of them would be I add 3, right? So to get here, I have to add 3. How do I get from 4 to 9? I add 5. How do I get from 9 to 16? I add 7. How do I get from 16 to 25? I add 9. So what would we guess would be the next thing in this sequence? In fact, what is it? It's 36, which hopefully is plus 11. It is. It's a miracle. Now, so do we see a pattern? So could we define a recursion formula? So if I say that the first thing in my sequence is 1, then how would I get the next guy? This, I have to be kind of careful here. Yes.
Do you need to write 8 and plus 1?
Oh, yes. I could either write it as an equals something with an minus 1, or I could write n plus 1 and use an. Either way is fine. So let's use an plus 1 since that's what I did last time. Okay, what do I do? Okay, so to get the second term, I need to add 3. To get the third term, I need to add 5. To get the fourth term, I need to add 7. To get the fifth term, I need to add 9. What did all of those just have in common?
And choose what you're adding.
Did I? Well, oh yeah, I definitely added 2 every time. But I'm saying, okay, this guy is associated with the number 1. This guy's associated with 2, 3, 4, 5. If I'm trying to get the second guy, I add 3. If I'm trying to get the third guy, I add 5. If I'm trying to get the fourth guy, I add 7. If I'm trying to get the fifth, I add 9. If I'm trying to get the nth guy, what do I add?
2n minus 1.
Boom, good job. 2n minus 1. Does everybody see it? So if I am trying to get the second guy, I double that number and subtract 1. If I'm trying to get the third guy, I double that number to 6 and subtract 1. I double 4, subtract 1. I double 5, subtract 1. I double 6, subtract 1. So what I want to do is I want to take whatever I had before, which I'll call a sub n, and then what I want to do is I'll add what? So what's the number that I added? So if I'm trying to get the second guy, the n plus first guy, let's say, and let's say that n was 1. So I'm trying to get the second guy. Then I double that number, whatever it is, and subtract 1. So I double n plus 1 and subtract 1. Let's see if we buy our own story. Let's say I was trying to get n sub 2. Then I take a sub, okay, let me just write this. So a2 needs to be a1 plus 2 times, well, what is n in this case? 1, because I'm getting n plus 1. So 2 represents 1 plus 1. So n is 1. So I get 2 times 2 plus 2 times 2 minus 1. But a1 was 1. So I get 1 plus 4 minus 1. So the second term should be 4. Correct? And what would be a3? A3 would be a2 plus 2 times, well, 2 plus 1, which is 3, minus 1. A2, we said, was 4 plus 6 minus 1, 9. Yeah.
So I think we can put down a different answer that might
Oh, yeah, I was thinking.
might pop out. That like you can do the square root of n absolute value plus 1 squared.
It might work. Let me see. So you said that a sub n plus 1 was equal to what?
Parenthesis, square root of a n absolute value of the square root.
Okay, like this?
Yeah, plus 1, and then parentheses squared.
Okay. That's funny. I see. Yeah, that is technically true. But what I like that. Because what you're doing is basically.
We're like, the gig's up, we know what you're doing. You're doing the square root of 1, the square root of 2, the square root of 3. So if we square root it, I don't know. Yeah, sorry.
Yeah, that's pretty funny. I don't think it's what they intended, but I do see what you're doing, and it works in this case because of the nature of the function that's being used. But yeah, it kind of feels dirty because what you're actually doing is you're kind of like, well, what got me to AN? Well, sort of in. And so just go back to in, add 1, and then square that guy. And so really what you're doing is saying, well, it's this, right? But I see, technically it's right. It's not wrong. That is a recurrence formula that works for this. But it's kind of like, I don't know if it was the, well, it's fine. It's fine. That's pretty good. I like it. Okay, let me see if some people are asking a question. Maybe not. Okay. What else can I do? This type of thinking is really, really important in computer science. So if any of you ever plan on taking Computer Science 201 or something, this kind of thinking is really important in generating like a recurrence relation. Like if you want to populate an array with certain terms that have a relationship as you go on, you've got to be able to build recurrence relations like this that generate a sequence. And yeah, it happens all the time in CS. Other questions? Yes.
42.
42. Okay. So this one, they say write out the first four terms. If the sequence appears to converge, make a conjecture about its limit. If you think it diverges, explain why. Okay. So we aren't quite to proving the official limit of a sequence, but we could maybe make an educated guess. So this is 42. We have a sub n plus 1 is equal to 1 minus a sub n over 2, where a0 is 2/3. Okay, and then it says find a1, a2, a3, a4 to start, and then see what you think about convergence. Okay, so we know the recurrence relation. We know what the first one is. We know a0 is 2/3. So the second one is a1, and that's going to be 1 minus a sub 0, which is 2/3, divided by 2. Correct? Which could be written as 1 minus 2 over 6, which is 1/3, right? So this is 1 minus 1/3, which is otherwise known as 2/3. Correct? Did I do that right?
Yeah.
I think so. Yeah, 2/3. Well, this makes my life very easy. Because if I plug it in again to the recurrence relation, I already know that if I plug in 2/3, I get 2/3. So if I plug in 2/3, I'm still going to get 2/3. So I don't need to recalculate this again. I can just say that A2 is 2/3, A3 is 2/3, and A4 is 2/3. And then the question would be, do I think that this sequence will converge to something?
I definitely wrote this problem down wrong, so I had a of 0 equals 2, so that's why I asked it. 'Cause
Oh,
it's
yeah.
going all over the place, so.
It certainly is more interesting.
This makes
All right.
a lot more sense.
Yes. It would be much more interesting if A0 were something other than 2/3. But maybe this is interesting in and of itself, that obviously this thing converges, and it
Yes.
converges to 2/3. Yeah. Very good. Okay, that's a good place to stop for today. Homework on this section will be due tonight by 11, and then we will cover the next section over 10.2, which I believe is also just kind of a continuance of our study of sequences. That will be due on Friday. So come Friday prepared to ask some questions over 10.2. Have a great day. See you then.